Dear colleagues, we present to your attention our work intelligent data selection in autonomous robot movement. Any autonomous mobile robot uses a lot of data sources to control its own position, its own location, events in the surrounding environments, and the results of its activities. To do this, it uses so-called sensors, devices which provides different kind of information about the environmental events. And the data flows from such sources. They have a set of properties which pose the necessity to make further processing, since we are error prone, often come with a very high rate and contain a lot of different kind of information. The number of these ongoing events, in principle, the number of events in the environment, it could be very large, but they have a different importance for the movement control. Some of them are very important, some of them are crucial, and some of them are absolutely insignificant or irrelevant to the autonomous mobile device and its activities. So we need a method to select important movements, crucial movements, and insignificant events, and give them sort of maybe rates. So in this work, we propose methods for intelligent data selection. The method is based on the well-known additive increase multiplicative decrease algorithm, AIMD. It is used in the data communication to provide a distributed control of data communication infrastructure. As for this problem, with increase and decrease rules which this algorithm defines, they could imitate the human cognition function. So they express the level of our pessimism and optimism about the environment and the activities of the autonomous mobile device, autonomous mobile robots. If we are optimistic about the environment, we increase some parameter, and actually we decrease the level of the observation. And if we are pessimistic, we have to watch the events more carefully, so we decrease the parameter, which increases the level of our attention. So through this algorithm, we try to imitate the human cognition function in its observation part. The goal of the method is to reduce the amount of data passed to the processing for the robot movement control, so to reduce the load of the fusion models and intelligent modules. And the effect is in filtering the most significant information. We consider a sensor as a mapping from SM space to SN space. Both spaces are real multidimensional spaces, and also they introduce a norm between 2 points in each space. The norm is additive, and also we could use a scalar multiplicator, which is also real. Traditional processing processing techniques, actually maybe not traditional, but widely used processing techniques normally are called smoothing. So smoothing raw data transforms the sensor data also into some another real space which which has the same dimension, and we call it SV wave, and also we define a sequence of measurements. So here you can see the upper level architecture of this filtering and smoothing approach. So first we have the sensor sets, it produces raw data stream. Then we have the primary smoothing filter, and then we have intelligent data selection, which produces selected data. The amount of data decreases in every step, and also we have a feedback. In some cases, no smoothing is needed, so we can avoid a primary filtering technique. And the main parameter of the algorithm is a delay, tau n, which is applied before the sensor data are passed to the inference model. The delay is dynamically adjusted, so it depends on the property of the data, and we use AI and the algorithm to make these adjustments. Here you can see the rule of this adjustment, so it's either decreases or it increases. The choice of a strategy depends on special, so-called special events. So we decrease the delay if special events has happened, and we increase the delay if no events has happened. So what are the events? We believe that we should decrease the observation level if the environment is stable and the autonomous mobile device operation also is stable. So our task is to find some moment when instability is about to start. And if the sensor is properly tuned and properly calibrated, it fluctuates around the average value, or so-called true value. And hence, if the sensor data start to decrease or increase monotonously, we can suspect that something is about to happen, and we have to increase observation effort, and also maybe use some inference or fusion technique to identify some important event. Also, if we have some big jump in the sequence, the situation also is, should be examined more carefully. Also, if we use a common filter or a particle filter, we use the error evaluated before a correction step to identify the event. And also we have a so-called list of a critical event which need immediate attention. On this, using this approach, we have developed an algorithm which implements a selection principle described above. The algorithm is described in detail in the paper, and here you can see the table of this presenting its input parameters, which is multiplicative decrease parameter, additive increase parameter, of the length of a meaningful monotonal sequence in the data stream, initial value of the delay, and the upper limit of the delay. It shouldn't be exceeded. Now the algorithm was applied to data set presented in the open free access machine learning repository. A link also is presented in the paper. We used from this repository, we used the data set of a single chest-mounted accelerometer. So the person which bear this accelerometer performs different kinds of activities like sitting at a desk with a computer, or standing up, walking and talking, climbing stairs, etc. To this accelerometer, uncalibrated accelerometer data, we applied our algorithm and try to see how it's able to reduce the amount of data and follow the main stream of the events. Is it's able to signal about some important events. Now on this picture you can see a smoothing example. So this smoothing was done by our algorithm. It is applied to the x-axis and m is 5. M is the length of a monotonal sequence, which is treated as significance. So you can see here that it's basically follows the values, and if they are stable, the delay increases. Now here you can see yet another smoothing example. It's for y-axis and m is equal to 3. Here this method successfully filters and outliers, which are here, here, and here. And the next picture is for z-axis. I'm sorry for this misprints. Again, outlier is successfully filtered, and the values, they actually follow the stream, but the delay increases. So here this is a single period, so all data between this moment and this moment are not passed to the inference modules. Okay, and now conclusion, we propose a new fuzzy method for intelligent data selection. Its novelty is in using additive increase, multiplicative decrease strategy from data communication. It's intended to detect the most significant information and tries to imitate human cognitive function, as I said before. It's implemented using the memory-saving algorithm with a linear complexity. This is our method, since it's very simple, so it could be implemented in a very efficient way. And also we propose several numerical examples that show efficiency of our method. Also, we plan to investigate analytical properties of the method, including the estimate of the maximum relative error, the average amount of selected information, and the average delay. Thank you very much for your attention.